All right, let's dive right in. As an aerospace architect, I can tell you that the future of flight, these quiet electric aircraft we've all been dreaming about, it all comes down to solving one fundamental problem. And it's not a small one. It's a massive physics barrier that we absolutely have to engineer our way around.
Okay, so here it is. This is the heart of the problem. We call it the energy density gap. And what you're looking at is a fundamental law of physics that we just can't ignore. On one side, you've got jet fuel, and on the other, our most advanced aviation batteries. It's not even close. This gap dictates everything. Range, payload, you name it. So, just how big is this gap we're talking about? Well, it's about 48 to 1. That's right, for the same weight, jet fuel packs almost 48 times more punch than our best batteries. This creates a huge operational headache for pilots and operators, what we call range anxiety, but on a whole new level.
So the big question is, how do you solve a 48 problem? You don't just throw batteries at it. Our solution, our gambit, starts with the hardware architecture. We decided to get the best of both worlds. And here it is, the P13 hybrid system. The simplest way to think about it, it's like a hyper-advanced hybrid car, but for an aircraft. You've got your internal combustion engine. That's your workhorse. That's for range. But then it's coupled with electric motors that give you that incredible, instantaneous torque and precision control you need for critical phases of flight like takeoff and landing. Now, this architecture gives us incredible flexibility. We can operate in 4 primary modes, and the system can switch between them seamlessly. We can go full electric for a quiet taxi and takeoff. We can run in series mode, where the engine just acts like a generator. We can go parallel, where both are driving the props. Or we can hit a boost mode and unleash everything for maximum power. It's all about using the right tool for the right job at the right time.
But here's the thing. All this amazing hardware complexity creates an immense control challenge. I mean, you've got multiple power sources, clutches, motors. So how do you manage it all? What's the brain of this operation that's making all the right decisions every single millisecond?
That's where the brains of the operation come in. We architected a dual-layered energy management system, the EMS. This isn't just a simple controller. This is the intelligent central nervous system of the entire vehicle. And we've literally designed it to think like a human brain. It has 2 layers. You have the strategic layer. That's the long-term planner, the part that thinks about the whole mission ahead. And then you have the tactical layer. That's the reflexive part, the muscle memory that acts instantly without even thinking. And this table really breaks down that philosophy. It's a clean separation of duties. The strategic layer, our far-sighted brain, uses a technique called model predictive control. It runs on a slow loop, maybe once a second, because it's looking at the big picture. The tactical layer, our fast-acting reflex, is running at 100 Hz. It's making 100 decisions every second, optimizing the powertrain on the fly. This is a perfect illustration of how those 2 layers work together. On the left, you can see the strategic brain planning the optimal battery state of charge over the whole flight. It's making sure we have enough juice left for landing. Meanwhile, on the right, the tactical brain is constantly tweaking the engine, nudging it into its most efficient sweet spot to save fuel right now, in this very second. And this setup lets us do some really counterintuitive things. For instance, we can use a little bit of electricity to actually make the engine more efficient. It sounds crazy, right? But by adding a small electrical load, we can push the engine into its absolute peak efficiency range, saving way more fuel than the electricity we spent. It's about thinking of the powertrain as one integrated system. Okay. So we've built a powerful, intelligent system. But in aviation, performance is meaningless if it's not safe. Absolutely meaningless. So how do we certify a thinking machine? How do we prove it's safe enough for people to fly in? And that is the million-dollar question for the regulators. How do you prove, beyond any shadow of a doubt, that a system that thinks for itself is safe enough for human flight? This is the hurdle we have to clear. And the bar is incredibly high. We have to demonstrate a probability of catastrophic failure of less than 10 to the -9 per hour. In plain English, that's less than 1 in a billion flight hours. That's the standard. It is non-negotiable.
So how do we meet that standard? Here's the core of our safety architecture. It's a mixed DAO strategy. Now, what that means is we isolate the complex thinking part of the software, the part that's doing all the smart optimization, and we run it at a lower design assurance level. And then we have a very simple, deterministic, and totally independent monitor built to the absolute highest standard, DAO A, that watches over it. Think of it like a simple, bulletproof guardian watching over a complex genius.
That guardian is the safety limiter.
Its job is incredibly simple. It just watches the commands coming from the smart system. If the smart system ever tries to do something that deviates from the pilot's intent, that limiter instantly steps in, bypasses the algorithm completely, and guarantees the system stays within a safe, predictable state. It's our ultimate fail-safe.
Now, a great design is one thing, but you have to prove it. So that entire safety architecture is backed by an extremely rigorous path to validation. We go from pure code all the way to what we call the Iron Bird.
We follow the industry-standard V-model development process. It's a simple but powerful concept. Everything you define as a requirement on the left side of the V has to have a corresponding verification and validation test on the right side. It's a methodical way to ensure we test absolutely everything we design.
And that validation process happens in stages. We start with model in the loop, or MIL, where we run thousands of purely virtual flights to test the logic. Then we move to processor in the loop, PIL, where we run the actual flight code on the actual flight computer. And the final step is the Iron Bird, a full-scale ground test rig where we integrate all the real hardware and deliberately inject faults to prove the system can handle anything.
So when you put it all together, you realize the EMS isn't just a component. It's the cornerstone of the whole vehicle. It's the intelligent system that integrates aerodynamics, battery physics, thermal management, safety, and even the commercial operation of the aircraft. It's what tames the complexity and unlocks the full potential of this hybrid architecture.
You see, the companies that truly master this kind of energy science, they won't just be building aircraft. They're going to define the future of flight. It's about more than just hardware. It's about making that hardware intelligent, safe, and efficient. It's the key to making this new era of aviation a reality.